Hello, let's learn about engineering approach to airborne infection and natural ventilation. Natural ventilation is created by the use of external airflow generated by natural forces such as flow of wind and differences in temperature. Natural ventilated rooms can achieve very high ventilation rates under ideal. The types of natural ventilation are stack effect, that is buoyancy, or wind driven, that is pressure. In stack effect, warm air, the principle is that warm air is lighter, less dense than colder air. Warm air hence rises, cold air falls. The intestinal chimney stacks can create larger differences between top and bottom, increasing the airflow rate. The wind-driven or pressure type of natural ventilation here is based on the principle of pressure differences, which results in air mass movement, pockets of airflow from higher to lower air pressure areas. So to wind-driven, the air moves from higher pressure to lower pressure. There is a cross ventilation that is ensured. While in stack ventilation, the colder air falls down and the warm air rises up and it is exhausted. So that's the difference between wind-driven. A natural ventilation mechanism it can be a combination of wind driven or a stack effect. If you see a wind driven effect, it moves from a higher positive area to a negative pressure area and it's exhausted outside. Stack effect, here the solar chimney effect is based on the stack effect, where the efficiency of the solar chimneys can be improved by increasing the stack height and increasing the temperature difference between the collector and the ambient air. Stack driving flows in building. Indoor air is warmer than the outdoor, and then with an indoor air temperature is greater than the outdoor, and in the stack effect, the indoor temperature becomes less than the outdoor because with the engineering controls. You can refer to the article on control airborne infection disease in ventilated spaces, Nielsen, for further details. Now, if you see the environment of office building, a BR is low energy fans are used on still air days, but glass are for solar heating of the thermal chimneys to produce the stack effect. Most cities, natural ventilation is the preferred method, which ensures efficient ventilation at all times in all climate conditions through proper operation and maintenance and by regular checks to ensure fixed unrestricted openings. Example: use of lower shutters instead of glass windows to ensure ventilation day and night. Then to maximize the natural ventilation, where air changes is not able to be measured, as is usually the case in rooms with natural ventilation, the following standards for ventilation shall be followed, such as opening on opposite walls, such as cross ventilations. Openings are unrestricted. 20% of floor space should be available. Window area on each wall. Upper levels of the building should be higher from the ground floor. And buildings and openings are oriented to use the prevailing wind without obstruction by other nearby buildings. So that's how we can maximize the natural ventilation. Have an unrestricted openings. 20% of floor space should be openable window area on each wall. That is the window areas, that open way area should be about more than 20% of floor space. Upper layer of the building should be higher. So natural ventilation issues are thermal conditions, weather dependence, measurement issues, management of openings, building structures, and others. How we can deal with it? Have measurements of air changes per hour at regular intervals and to ensure the ventilation. Calculate the air changes per hour is the simplest way to assess the ventilation, where air changes per hour is the volume of the air moved in 1 hour, and 1 ACH means that the volume of air in the room is replaced one per in 1. The type, based on type of healthcare setting, the registration room should have more than 6 engines per hour. Inpatient department more than 6. But high risk settings should have more than 12 engines per hour. That is like TB departments, tetanus and TB wards, airborne infection isolation room should have more than 12 engines per hour. So when we have more 12 engines per hour, the 99% of the air in the room gets the time required for the removal of the droplet nuclei is about 23 minutes for the air room for the air changes air of 12, while it is 35 minutes to remove 99.9% of the contaminated air. So measurement of the air velocity through open window can be done by this manometer. Never put the fingers on the open space, and when a manometer can be used for the measurement of the air velocity. The measure dimensions with a speed we measure scale, and wherein the area of the window opening should be measured with the formula length. Calculate the room value with the same scale with into depth into height is the formula for calculating room. The room volume and we have the window area. The air velocity is to the window using a manometer is calculated. So the formula is air flow rate is into the window area into the air velocity. Window area is formula is length into width. Air velocity is measured with a manometer. The room volume is width into depth into height, that is 45 meters cube. So for the particular room. So air changes per hour is air flow rate divided by the room volume. What's wrong in this picture? Very poorly ventilation blocked windows, ineffective ventilation, crowded waiting areas, exhaust fan will draw air from the waiting to the doctor's chamber, from the doctor's waiting from the doctor to doctor's chamber, poorly ventilated room. Similarly, from the picture, you can see a poorly ventilated waiting area in outpatient clinic. So it should be such that there are more areas of openings and the airflow should be from the clean to dirty. Maximize the natural ventilation in the waiting areas, as we can see where the waiting area is in the open air and there are open spaces with maximum windows. Three windows which are where there will transfer into the doors. So the conclusion is that ensure adequate airflow and minimal flow specifications are made. Appropriate measurements under all conditions are as required. Flow direction should be from clean to dirty. Flow direction should be away from the infected. That should be verified. Ensure and verify the consistency under all seasons. Avoid flow towards the patient and especially susceptible.